Hey AP Chemsters, this is Mrs. Vandeloy bringing you 9.9 Part 2 of the Blank Wall series. We just finished about resonance, and that's when we had two or more correct Lewis structures for the same ion or the same molecule, if you will. And when we talked about resonance, we said, well, really it is an average of the structures. Well, that happens a lot, but sometimes there is actually a preferable arrangement to these structures, and we'll see which ones maybe are the best, and we'll do it by formal charge. So kind of bear with me. We're going to set up, well, why do we talk about formal charge? What is formal charge? What are the rules for formal charge? And then towards the end, we'll show you the power of formal charge and what it really does for us, okay? So first, let's define it. It's a fictitious charge assigned to each atom in a Lewis structure that helps us to distinguish among the competing Lewis structures offered by resonance. So we're actually seeing which ones of the Lewis structures are kind of like the best, okay? The formal charge of an atom in the Lewis structure is the charge that it would have if all the bonding, it should be electrons, I spelled that wrong, were shared equally among the bonded atoms. So it is the calculated charge for an atom if the effects of electronegativity are ignored. And what does that mean? Well, we know something about fluorine. Fluorine is the most electronegative element. And for that reason, we talked over here, if fluorine is more electronegative, it has a dipole moment. Remember these partial charges, it should say partially positive. That's two boo-boos I see right here now. I have spelled electrons wrong and I have an equal sign. All right, so make that a partial positive. So we can say here this is a partial negative and this is a partial positive. That's not what we're talking about, okay? Formal charge is a fictitious charge assigned assuming that electronegativity is ignored. So that's not what we're talking about. So what is formal charge? Well, there's a formula for it. And the formula for it is right here. It is the number of valence electrons, that's why it's so important to know your number of valence electrons, minus the quantity of non-bonding electrons. Those are usually your lone pair electrons, plus half of the bonding electrons. Okay, so let's check this out. Here, let me do something real quick. Okay, so in terms of HF, again, we need to find the formal charge of both hydrogen and fluorine. Okay, and you'll have to do that for all atoms in whatever the ion or the compound is that you're asked for. So let's look at hydrogen first. Well, how many valence electrons does hydrogen have? Hopefully you're looking at a periodic table and you'll see it's in the first column. It has 1 valence electrons. And then what? Well, how many lone pairs does hydrogen have? Do you see lone pairs around here? I don't see any around here. Hydrogen will never have lone pairs. So if you're ever finding the formal charge of hydrogen, it should always be 0. There are no lone pairs. Okay, and then what? We'll have these electrons here. These are my bonding electrons, and so the idea is, well, half of those, that pair, came from hydrogen. So that's why there's a 1/2 of the 2 here. And if you do the math, a half of 2 is 1, 1 plus 0 is 1, and then so this whole quantity here is 1, 1 minus 1 is 0. Okay, let's check out fluorine too. Hang on a second, let me erase this a little bit, and let's see what we do for fluorine. Well, how many valence electrons does fluorine have? Are you looking at your periodic table? It's in group 17. Hopefully you know it's 7. Okay, then what? How many non-bonding electrons you have? How many lone pairs you have? And do you see these right here? These are my non-bonded electrons. And if you count them all up, that's your 6. And once again, the same number of bonding electrons right here. Okay, those are my 2. And let's see what happens. Well, what's half of 2? That's 1. 6 plus 1 is 7. This is all 7. 7 minus 7 is, once again, 0. Okay, and what does this tell you? If both atoms are 0, it's probably the most ideal structure you can make. That's really what that kind of means. There are some rules of formal charge. The sum of all the formal charges in a neutral molecule must be 0. If not, you made a boo-boo. Sum of all formal charges in an ion must be equal to the charge of that ion. If not, you made a boo-boo. Small or 0 formal charges on individual atoms are better than large ones. So, what does that mean? These zeros here are pretty preferable, okay? They're better than bigger numbers, okay? When a formal charge So it says when formal charges cannot be avoided, negative formal charges should reside in the most electronegative ion, or excuse me, atom. So what does this mean? If they're not all zeros and you get something that's a negative, it should be on the most electronegative element. So fluorine, your chlorine, your oxygen, okay, those should have your negative charges. So it says two structures of HCN exist, all right, which is your best representation. This is the power of formal charge. We're going to determine if my central atom should be carbon or should my central atom be nitrogen. Okay, and by determining the formal charges, we will know. So let's go ahead and do this. How many valence electrons does hydrogen have? Well, hydrogen has 1. Minus. Okay. How many lone pairs are around hydrogen? None. It shouldn't be. Okay, then what? How many bonding electrons are there? That's what this number right here would be. So there's 2 there. And I add that all up. So half of 2 is 1. 1 plus 1, or 0 plus 1 is 1. 1 minus 1 is 0. Okay, let's try nitrogen. Well, how many valence electrons does nitrogen have? Nitrogen has 5. Okay, how many lone pairs are on this nitrogen? I see 2 right here. Okay, how many bonding electrons do we have? They're right here. So a half of 6, that's a half. Okay, so what's a half of 6? It's 3. 2 plus 3 is 5. 5 minus 5 is 0. Okay, let's try carbon next. How many valence electrons does carbon have? Carbon has 4. How many lone pairs are on carbon? 0. Carbon typically doesn't have lone pairs. I don't know if you've seen that. Okay, then what? How many total bonded electrons do we have? Well, we have 2 with the hydrogen and 6 with the nitrogen. That's a total of 2 plus 6 is 8. Okay. And then what? Half of 8 is 4. 0 plus 4 is 4. 4 minus 4 is 0. We have all zeros. Okay, that looks pretty good. Let's check out the next one. Well, hydrogen really hasn't changed. So if you notice, hydrogen has 1 valence electron. It has no lone pairs, and nor should it, right? And it has, it's a plus here, and it has 2 bonded electrons, and if you add that all up, you get 0. Okay, that was good. Let's do nitrogen now. Okay, so nitrogen has 5 valence electrons. It has no lone pairs. Oh, okay. And then what? Oops, that should have been green. Sorry, guys. Plus 1/2. How many total bonding electrons are around nitrogen? There's 8, so half of 8 is 4. 4 plus 0 is 4. 5 minus 4 is 1. Oh, that's not a 0, is it? Let's try carbon next, okay? Carbon has 4 valence electrons. How many lone pairs does it have? 2? Well, that's not very common, is it? No. Should be a clue right there. Okay, and then what? How many total electrons is it bonded with? There's 6 of them. Okay, so what's half of 6? You knew that was 6, right? There's your 6. Okay, what's half of 6? It's 3. 2 plus 3 is 5. 4 minus 5 is -1. Now, let's check out our rules here. The sum of the formal charges in a neutral molecule must be 0. Well, this is a neutral molecule. Okay, there's my rules there. So 0, I'm looking over here. 0 plus 0 plus 0 is 0. That works. 0 plus 1 minus 1 is 0. So, good. Rule number 1 works. It's not an ion. The small or 0 formal charges on an individual atoms are better than large ones. All right, so notice that in the first structure, they're all zeros. Notice that in the next one, they're not all zeros. So the smaller the numbers, the better. And so it looks like structure A, or if I call this one A and this one B, structure A looks better than structure B. Let's look at the fourth rule here. When formal charges cannot be avoided, meaning there's something besides 0, negative formal charges should reside in the most electronegative element. Well, look over here. Your negative charge, formal charge that is on carbon. But what other element is in this compound here? Nitrogen's there. What do you know about nitrogen? Nitrogen is one of the big four. It should be one of the most electronegative elements there are, and yet it has a positive one and carbon is a negative one? No. So which is your best representation here? It's clearly going to be A, okay? Your first clue is that you have all zeros. That's a huge clue. Your second clue is that your negative is on carbon. If you have to have a negative, it should be on your more electronegative element, which is not carbon. So A is really your best answer. So that's the power of formal charge. So how do you know that carbon's your central atom? You find your formal charges and then you figure it out. So let's see what the next part is. Well, notice there are three possible structures for the cyanate ion. No, it's a cyanate. We usually don't think of cyanate. Cyanide is Cn negative. Cyanate is OCN negative. So we have three different elements, and so that kind of gives you an idea that we need to know the formal charges here. Two, not so much. Three, yeah, you better look at them. So I have carbon in the middle each time, but look, we have either a single and a triple bond, two double bonds, or a triple and a single bond. So which is our best one? Okay, well, let's do, I'll do the first one and let you try the next two, all right? So here's oxygen. Oxygen has valence of 6. Hopefully you have your periodic table, so you knew that. All right, and then what? How many lone pair are on oxygen? I see right there, I see 6 of them. Okay, how many bonds are there? Oops, I should be doing this in blue here. Here we go. Those are my only bonded electrons. There's 2 of them there. All right, so a half of 2 is 1, 6 plus 1 is 7, 6 minus 7 is negative 1. All right, that's not too bad. Why? Because I know oxygen's pretty electronegative. Let's try carbon here. So carbon has 4 minus, how many lone pairs are on the carbon? None. Okay, that's good. How many total bonded atoms are there? There are 2, 4, 6, 8. Okay, so a half of 8 is 4, 0 plus 4 is 4, 4 minus 4 is 0. All right, let's try the nitrogen one next. We have a valence of 5. How many lone pairs are on this nitrogen? 2. All right, and then what? We have total of 6 bonded electrons here. See those? All right, so oops, a half of 6. That's 3. So 2 plus 3 is 5. 5 minus 5 is 0. So that actually looks pretty good. So if you add them all up, you get a total charge of negative 1, like it should be. Okay, oxygen is the most electronegative element in this set here. All right, only fluorine is more electronegative than oxygen, so it gets the negative. That looks pretty good. Why don't you pause this, and I mean it, you try doing this on your own, and then let's come back and see how you did. Okay, so pause this. All right, so this is what I came up with. I got 0, 0, negative 1 for structure B, and I got 1, 0, negative 2 for structure C. Well, let's check out and see if the rules work. So rule number A, or number 1 from the prior page, doesn't work. It's not a neutral atom. These are ions, so look at rule number 2. Do they all add up to negative 1? A does. B, 0, 0, negative 1 does. 1, 0, negative 2 adds up to negative 1, so that works. Is the lowest set of numbers working? Well, it looks like A and B has the lowest set of numbers. C, you got a 1 and a negative 2. That's not as good as zeros and negative 1s. So then, how do I know which is better between A and B? Okay, well, which is your most electronegative element? A or oxygen, carbon, or nitrogen, and hopefully you know it's oxygen. Okay, fluorine is the most, then oxygen. Nitrogen and chlorine are tied for number 3. After that, you probably just have to look at a periodic table to know. So I'm looking at oxygen as the most electronegative element, so it should have the negative formal charge, and A has oxygen having the negative 1, and letter B has nitrogen being the negative 1. So that is going to help us which resonance form is likely to contribute most do the correct structure of the sin A ion. And here, hopefully you say it is A. Why A? Because of the rules, okay? Because it has the lowest set of numbers and the oxygen has the -1 formal charge. I'll put FC here. Formal charge, not FC Cincinnati. Okay, so why don't you go ahead and check out the next one. Assign the formal charges to each atom of the resonance structure for N2O. It says, look at problem 22A for the 3 different possible structures. Oh, that was the problem right above this. Then determine which resonance structures is likely to contribute the most to the correct structure of dinitrogen monoxide. Please pause this. Please actually do this on your own. Just don't watch me do it. You learn a whole lot more if you try it first and then see if you got it right. So pause this and let's see how you did. So here are my 3 structures. Again, notice I used 22A as a guideline. I have a single bond and a triple bond, 2 double bonds, and a triple bond and a single bond. And I labeled the nitrogens 1 and 2 so we can keep them straight. And you can see in the first case I got -2, 1, 1. It doesn't look so great there. There are not any zeros there. It doesn't really help. But they do add up to 0, which is a good thing. The second structure has -1, 1, 0. They're a lower set of numbers, which is good, but nitrogen has a -1 and a +1. On the other one, we have nitrogen 0, nitrogen 2 is 1. Ooh, and oxygen has -1. So which one of these structures is the best? What do you think? Well, I think it is structure C, if you will, if I call this letter C right here, okay? Why would that one be the best? Because I have the lowest set of numbers, and look at this number right here. Oxygen, the most electronegative element in this set, has your negative formal charge. So this is probably the one that contributes the greatest to the correct structure, okay? So not saying that these two never occur, one A and B, I'll call it A and B, but C seems to be the one that is likely to contribute to the most. Okay, so it's not a 50-50 or 30-30-30, or, you know, if you know what I'm talking about, distribution. It probably C as the one that spends the most time being. Okay, let's see what problem 22C is all about. Oh, this is a great one here, okay? So probably when you had first year chemistry, we probably saw, the sulfate ion. It works if you count up all your charges, or excuse me, all your electrons, if you would. So if you want to count them up, it's 6 plus 24 is 30, plus 2 extras, 32 electrons. Structure A has 32 electrons, and check out structure B. I think it also has 32 electrons. So both of them fulfill, at least the correct number, but let's assign formal charges, okay? And so if I were you, if I have S, O, and then O. Well, Mrs. Vanderley, there's 4 O's. Yes, I understand that, but these are all the same. These are actually, I probably don't need to do all those O's, okay? They're all the same O. Okay, but over here I do have 2 separate O's. I have a single bond and a double bond O, and let's check out what happens here. So each of them have 6 valence electrons. Okay, how many lone pair are on the sulfur? None. Okay, then what? I have 8 bonding electrons, and so if I were to do all that, I think I get a 2. What about oxygen? All right, let's see here. We have, let's go back here. I have 6 valence electrons on those. Okay, then what? I have 2 bonding electrons. Okay, and then what? If I add that all up together, I think I get a -1. Okay, and does that make sense? Well, if I were to add them all up, if this is a +2, -1, -1, -1, -1, does it all add up to -2? Sure does. That's the charge. So far so good. Let's try this one. We all have 6. Okay, and then look at the sulfur. It has no lone pair. The single bonded, so let's use this one. Here's my single bond. All right, it has 6 lone pair, and here's a double one. It has 4 lone pair, or I should say lone pair, but 6 electrons, 3 lone pairs. This one has 4 electrons, 2 lone pairs. All right, and now let's see here, 1/2 of 8. And I still get a 2 here. That didn't change. Over here, for my single bond, I'm up doing this again. There is, what is that going to be? Hello, 2. And that's going to be a -1. Works out. And what about this next one? It has 4. Okay. And then what? We have, well, what does that equal? Oops. Hello, come here. There we go. What does that end up equaling? 1/2 of 4 is 2, plus 4 is 6. Oh, I'm sorry. These are minuses, aren't they? Oh, Mrs. Vanderwally. These should be all minuses. That's my mistake. Go back and fix those. Does that still work? 6 minus 4 is 2. Yes. 6 minus 7. Oh, that works. Okay. And so what does that tell you here? Okay. Does this make sense to you? Well, so does this make sense? The answer is no, it doesn't, because the first thing I know is I had to make a mistake. I had to make a mistake because it doesn't add up to -2. So if I were to, use the numbers I came up with, what just happened? This is a +2. Oops. This is a 0, this is a 0, this is a -1, this is that has 0, doesn't it? Not -2. And I don't know if you caught my boo-boo. I did. It's right here, isn't it? Which makes this wrong. How many bonding electrons does sulfur has? It's not 8 like the one before, silly Mrs. Vanderwally. All right, how many does it actually have? Is 2, 4, 6, 8, 10, 12, doesn't it? Did I count that right? Hopefully I counted that right this time. No, it isn't it? Yeah, it's 12. Hello. So now what? Well, what's 1/2 of 12? 6. 0 plus 6 is 6. 6, this is a minus. 6 minus 6 is 0. Oh, and now it makes a whole lot more sense, because if the sulfur is actually 0, and my single bonds are -1, and my double bonds are 0, it has what? It has more closer, or formal charges closer to 0 than this structure does. Okay, I have 2 zeros and a -1. Here I don't have any zeros. Okay, so this actually, believe it or not, is the best structure. Okay, and it probably spends most of its time in that structure. And how can this be? Well, think of sulfur. Sulfur is in the 3p subshell, which means it can expand into its 3d subshell, and so it doesn't have to fulfill the octet. It can go beyond the octet and show this kind of a structure instead. So what are you telling me, Mrs. Vanderwally? Do you think other elements could do this? Could phosphorus perhaps do this? All right. Yes, it can. Okay, so if you're in the 3p, the 4p, the 5p, you can expand the octet, and by doing so you actually get formal charges to be closer to 0. So I'm glad I found my boo-boo. I'm glad that we have this all straightened out, and I'm glad you stuck with this. So once again, don't wait to be great, and I hope this helps. Talk to you later.